This will be part of my problem series. In this video, before looking at the next set of problems, I want to look at the process of loop or mesh analysis because they will involve this type of analysis in our next series of problems. Once I am finished with this series of problems, I'll be posting them in my stand store at this web address. Before proceeding, I want to explain the three web addresses that you will be directed to using. You have already seen the first here. This is a web address of my stand store, which will give you direct access to all of my electrical courses. On the last page, you'll find an address that will direct you to obtaining the 50-page crib sheet and notes that will not only be handy when you're taking my courses in my stand store, but also for reference during any time during your career. Here you'll also be asked for your email address, which will not be shared with anybody or distributed in any way, but it will allow me to keep in touch with you and let you know of any additions or updates to my courses and or blogs. Near the end of the video, I'll be introducing you to a supplier of electrical products, which in my estimation are of value worth paying attention to. I'm going to go through the theory first, very quickly, and then I'll analyze some circuits, so you'll get the feel for this mesh current or loop analysis process. Mesh current loop analysis, by virtue of its name, analyzes a circuit that looks essentially like a mesh, and a mesh has several loops in it. In this case, this example has 3 loops, and we're going to call them loop number 1, loop number 2, and loop number 3. It goes without saying that there is going to be current flowing in this circuit because of the voltage supplies and the batteries that are present in the circuit. To start, we consider currents flowing in each of the loops. I'm going to make an assumption right now that the current flowing in loop 1 looks like this, and I'm going to call it I1. The current flowing in loop 2 looks like this, and I'm going to call it I2. The current flowing in loop 3 looks like this, and I'm going to call it I3. There is one current for each loop. Once we've made the assumption of the currents, we very quickly can formulate a set of mathematical equations based on Kirchhoff's voltage law, which you will soon see that can be analyzed and come up with the values for the currents. If we have assumed that the currents are flowing in the wrong direction, then the answers we get for those currents will come out negative. I'm going to assume my currents are flowing in a clockwise direction in each one of the loops. I could have made the assumption that they're flowing in the reverse or opposite directions. It doesn't matter because the mathematics will look after it. For now, I'm assuming I1 is flowing clockwise and I2 is flowing clockwise and I3 will also be flowing clockwise. The current flowing through the bottom resistor looks like this, and we're going to get a voltage drop across it as I've indicated, with a plus minus and a resistor in the loop of the 3 meshes because of the current I2 flowing in that direction will set up a voltage drop from positive to negative as in the diagram. And in loop 3, the outermost resistor, because of the current I3, will have a voltage drop as indicated, plus to minus. Now, looking at the common resistors, the common resistor between loop 1 and loop 2, the current flowing in that resistor will be I1 minus I2. I2 is minus because it is flowing in the opposite direction to I1. Again, it doesn't matter whether I1 is greater or less than I2, because if it turns out that I1 is smaller than I2, then our answer will come up such that I1 minus I2 will be negative, and I'll know the assumption direction or the assumed direction was wrong. But for now, my assumed direction of the current I1 minus I2, the current flowing in the common resistor, will be left to right. The current flowing in the common resistor between loop 2 and loop 3, I2 minus I3, is assumed to be flowing from the top to the bottom, and the current flowing in the common resistor between loop 1 and loop 3, I1 minus I3, is also assumed to be flowing top to bottom. As you can see, the assumed directions of the current flows determine the voltage drop polarity of the resistors. Once we have assumed the current directions, we then write the Kirchhoff's voltage law equations for each of the loops. Remember, Kirchhoff's voltage law states that the sum of the voltage drops around a loop must add to zero. So we will go around each loop using the assumed current flows and write down the voltage drops for that particular loop using that current. Voltage drops across each resistor whose voltages are given by Ohm's law and will carry a plus sign. Voltage rises, negatives to positives, as in the case of voltage supplies, such as batteries, will be indicated as negative voltage drops and will carry a minus sign. For loop number 1, starting with the voltage supply E2, we get minus E2 plus R2 times the quantity I1 minus I2 plus R5 times the quantity I1 minus I3 plus R3 times I1, which equals 0. We can expand by removing the brackets to get this equation, and finally collecting like terms, we get this equation. For loop number 2, starting at the voltage supply E1, we get minus E1 plus R1 times I1 plus R4 times the quantity I2 minus I3 plus R2 times I1 minus I2 equals 0, which we expand by removing the brackets to get this equation, and finally collecting like terms to get this equation. For loop number 3, there are no power supplies in this loop, just voltage drops and voltage rises across 3 resistors. Starting with R6, we get this equation, plus the voltage drop R6 times I3, minus the voltage rise R5 times the quantity I1 minus I3, minus the voltage rise R4 times the quantity I2 minus I3 equals 0, which we expand by removing the brackets to get this equation, and finally collecting like terms to get this equation. We are now left with 3 equations in 3 unknowns. The 3 currents are the unknowns, I1, I2, and I3. Our known quantities are the resistances, R1, R2, R3, R4, R5, and R6, and the voltages of the power supplies, E1 and E2. We now have 3 equations and 3 unknowns, so mathematically we can solve for the 3 unknowns, which are the 3 currents. I want to introduce you to another product that's out there that is worthy of paying attention to. The 𝐃𝐈𝐒𝐂𝐋𝐀 solar generators are available in various capacities. Depending on the running and starting watts required, you can choose the right size of solar generator. For example, you can choose a small solar generator if you want to run laptops or cell phones, or perhaps a small freezer. On the other hand, a large solar generator would be ideal for extended power outages. To find out more about these battery generators and to keep up to date on any sales or discounts that are available, simply go to this web address. And remember, this video has been brought to you by PSPT, where you will find electrical training videos when you go to this web address, which will also give you a free copy of my 50-page crib sheets that you can use while viewing any of my courses, or just keep it handy during your everyday work.